So this is some fourth part of the recitation, and we are going to talk about the relativistic momentum. So as you may all have figured out, we change the time and length and mass and this and that quite a little bit in this course. So quite frankly, we also have a new definition for momentum. This is the equation for momentum that we all know and loved. So this is going to be changed by a gamma factor. Why, you may ask, is that we might have this little experience that we have conducted, that we have like two balls that are colliding in y direction, that none of the reference frames that we used moves to. So we have our frames of reference like this, and let's say the primed one moves with velocity, with some velocity, and these ones are, for simplicity, are colliding in the y direction, and this length is to be capital Y. So what are they going to do is that we can just take this line to be the axis of collision, and then they're going to reach this axis of collision, then they are going to rebound, and then we are going to measure the time that they have rebounded. So our particle A, the velocity of our particle A, that's VA, is measured in the S frame, and the particle B's velocity is measured in the primed frame. So it's kind of like it just goes into y direction in the primed frame. So what we have around here is this, that we have this time y divided by VA. This is the time that it takes for A to just go to the collision point and rebound back to its original point. So this is what happens. And then this is going to be the same for VB as in the prime frame. They it kinda has this speed. So but what we are going to have is this other time that is measured in V, in S, I'm so sorry, in S, that is this one. So in S we measure some time, this t, like this, relevant to the velocity that we measure. But then we had this proper time that we measured in the S prime frame. So what we know is the time dilation formula. Right. This is the gamma t0, and this is dilated time, like this. So as we all know this, now we are going to pull VB to the side. This is like y over t, and then we are going to stick this in here. VB equals y over gamma t0, and quite frankly, that we also have VA defined as y over t0. Now, if we check this out, then we see that, let's assume for simplicity that MA and MB measured in the S frame is equal. But then, what about their momentum? MA and BA, which is going to be MA Y T0. So, and PB, MB, VB is going to be MB Y over gamma t0. Now that, notice this gamma factor over here. So it means that the speed of the frame actually does something to the momentum, and we have to counteract this because we have to conserve momentum. So if we just say that if we're going to measure the masses equivalent, how are we going to actually conserve momentum in an elastic collision? We could have arranged masses in such a way that masses are related this way, but then that would have been just a weird way of measuring mass. Like we can't really dictate just because we are going to conserve momentum. We are not going to dictate something like that. So what we are defining is that we are dictating this directly onto momentum. So like we don't know if this is accurate yet. So like we can't just say that every mass has to be measured that way. But we can dictate that in order to conserve momentum, we have to multiply it with some gamma factor so that all the laws of physics hold the same and whatnot. And how we move into this, now that we have this relativistic mass concept. So now that actually now we could actually say something like there's this relativistic mass that changes depending on the speed of the frame that it's measured in. But we actually don't need to use it, because in order to use mass, we could also use the momentum so that everything is compact and all together. So let's demonstrate this. So we are going to work on relativistic second law, Newton's second law. So this is a good one, dp dt. So in your book it is derived pretty clearly. So how to derive this is basically, now if you are not going to change mass in time, just take it out, and gamma n nu, because speed can change in time, because if there's no speed that's changing in time, there's not really acceleration over there, which obviously is let me not go into detail of this. So now that we have written it more openly like this, we could just take the derivative and then find that we have over this little gamma factor over here, and d nu dt. If we define this as acceleration, what we find is this a gamma. Okay. So what we're writing here is that we define acceleration in terms of mass. So what's going to happen is this: if we have constant f and some constant mass, then as the speed of our reference frames goes high up, like not to infinity obviously, but to c, and this gamma factor being like this can never, like it's can never reach 1. So obviously what we are going to have is that under constant f, as the speed of s prime increases, acceleration decreases, which makes sense, because otherwise if you had a particle p in space, and if you have applied some constant force, and if it kept accelerating, it would have reached c and passed the value of speed. Like, and this is actually the speed limit. speed limits condition. So all makes sense. Great. So I advise you to actually go to 1.8 of your books, mass and energy, and work out the kinetic energy formula, that is the line integral of the force along the line that it is applied. So one must actually, the calculation is pretty straightforward, but what I want you to consider is specifically this, is that let's say that you have this quirky C and you are applying some force to the particle along C, and you have some sections of C that are called like ds, little ds's, and then on this line the direction of force can change and whatnot, and you know how to apply the dot products and actually find the component of the force that is going to move this through the curve. So what you're supposed to realize is that this any such curve can be mapped into some line, some interval in the real line, and then you can just simplify this formula like this, f ds, right? So just take a line and map it into some real line, the segments of the real line, and change the force accordingly. You can do this. It is just parametrizing some simple curve. And then after you parameterize this, you're going to obtain this formula, mv dt ds. So as you may see, ds is our integration factor, and then we can just switch its places, right? We just switch. So gamma being a constant of nu, it just has to stay, and m just being constant over there, it just goes out, and this is obviously speed. So you put there this velocity, and then you take m out, and you are left with this thing. So Godspeed. After this, the calculation is pretty easy. Oh, also you could also show that kinetic energy in low speeds just reduces down to the classical limit. Reduces to the classical limit at low speed. It's pretty easy to work. Oh, and then one last little detail about all of this is energy and momentum. How do we relate energy and momentum? So basically, we obtain the formulas like this, and so if you have completed all this equations of the chapter 1.8, you have seen the total energy formula, which is just like this. Let me write it down. This is the kinetic energy that is written like this, and hence it's actually total energy, kinetic energy and this is the rest energy. So how do these relate? So what you actually do is that you take the squared norm of both of these things. So take the squared norm, m squared c4. This one. Take the squared norm of this, square, new square, this one. So now you're going to see that if only you had a c-square factor overall, you could add and subtract all of this. So if you had a c-square factor here, it's going to be in the same dimensions as the energy norm. So let's just do it. What you're gonna have is this. M squared c4 gamma squared minus m squared mu squared. So actually perfect. So what you have here is this, basically. I'm going to have squared c4. This is m c squared squared. Perfect. So so this is actually the energy momentum formula, and one can easily see what this means, right? So it's pretty easy. Now that we have some total energy of E, and this is our rest energy squared, and this is some factor related to our momentum, then we realize that some particles don't have mass, which is going to result in their rest energy being 0. So, but it is not going to require that their overall total energy is 0. We still have this factor. So what is going to happen is that their energy is going to be proportional to whatever momentum they have multiplied with c squared. So it's going to be like, if these things don't really have mass, then they are moving in speed of light, which is quite reasonable. So what we are going to have is that we can obviously state that for energy of the massless particle is this. So I'm going to have this chapter finished here, but if you have any questions and anything, you can always mail me. So as I said, we probably are going to have a live session where I am going to actually tackle problems, and I'm just going to add some quick reciting of the chapter 2 and 3 after this one. So maybe see you next time.